introduction, and thanks in particular to the organizers for creating this wonderful conference at such a nice place. And opportunity here to present a work which was done with two great collaborators, Gleb Kutuzov and Sylvain Lacroix, who are both here in the audience and who will be able to answer questions probably better than I can. And so yeah, what I will try to do is give some overview of this work. I should apologize, there are I think very few here in the audience who may have heard a rather similar talk already. I simply felt unable, say, putting myself the task to give an overview of this talk, to change it very substantially, so bear with me if you've heard it. All right, so let's jump into the scientific matters. Why? Well, I don't want to sort of motivate why nonlinear sigma models are important. They are, of course, kind of ubiquitous as models of quantum field theory. It is important to understand them if you want to understand ADS-CFT correspondence in depth, and so on and so forth. Rather, I want to remind why this is still a challenge after many years of time to quantize and really solve them in great detail. So what are the troubles that we have, at least with many nonlinear sigma models? There are some exceptions where life is better. All right, so I mean, as I'm sure all of you will know, we have many models where we're lucky to be able to start from a zero curvature representation of the equations of motion. So there's a Lex pair like here, so we encode the degrees of freedom of our model, the dynamics, I mean the dynamic degrees of freedom into two matrices, Lx and Lt, describing flat connections in either spatial or time-like direction, and integrability is coming from the fact that these are flat connections, which in particular implies that if we take, for example, here integrals along a spatial slice, the path-ordered exponent of this spatial part of the connection will be a generating function of conserved quantities after taking a trace. And well, everything is great if one, well, still may be very complicated, but I mean, typically a very good first sign is if you find classically, using the Poisson brackets of the degrees of freedom that are forming these Lex matrices, take this wonderfully simple and nice form, some quadratic Poisson brackets where the Poisson bracket of the matrix elements at the spectral parameter value lambda with those are some quadratic expression in the matrix elements are here somehow shifted around by some purely numerical matrix. Okay, if we have this, then the quantization is well understood. It leads to quantum groups. There is a whole machinery and a large set of good mathematical tools which one can apply then often, but of course not so often even in the quantum case and in the continuum theory. It's still difficult, but that's not the theme for today. The point here about sigma models is that the Poisson bracket isn't that simple. Namely, if we would, in the case of sigma models, typically take the Poisson brackets here of Lex matrices with themselves, there would be delta prime distributions. And that is a big problem for the computation then of the resulting Poisson brackets of the monodromy matrix. It's basically ill-defined, and people have tried hard to use the Poisson brackets of the Lex matrix as the basis for the definition of some Poisson brackets of a form like this or some generalization thereof. But this is where sort of the story got stuck somewhat. This is what is called the locality problem. So this is also sort of a locality problem of a sort. Yeah, and so, I mean, this has led to the speculations that maybe all these nice connections to quantum groups and so on might simply not be the way to go for the case of sigma models, but that one might need other tools, other techniques. All right, so this is a kind of reminder of why sigma models are hard from this point of view of, say, inverse scattering or quantum inverse scattering method, where somehow this relation and its quantization would play the basic role. We want to consider a particular class of examples where maybe first steps can be taken to overcome such problems. That is the idea. We're looking for some sufficiently rich, but also yet still sufficiently simple examples where one can maybe make a case study for possible other approaches to this problem, which go a somewhat different way than the traditional one. To explain what I mean by this. So here, I mean, this slide is full of complicated formulae. You won't really need to digest them in full glory. So let me just walk you through the most essential points here that will be relevant. So what we're defining here, and actually it might be better, I just realized, to start down here. So we want to consider a theory whose fields or whose degrees of freedom are encoded in some 2x2 matrix that we call G. And for this, with a little bit of fancy notation, we can write down an action. Don't worry so much about the details, but what is important is, okay, degrees of freedom are in this matrix function G, which is of course a function of space and time. And secondly, we have two parameters here which are introduced with some Lie algebraic tool. So there are some operators here acting on the Lie algebra by a joint action and so on. I really don't want to talk much about the details of this definition. We have an action, okay? That's the main point that we shall need here. And the action depends on two parameters, well, really three parameters. There's a constant k, which you can, of course, relate to h bar in front of the action as usually. This has an alternative formulation as basically, using some gauge symmetry, where we basically double the fields. We take two Lie group valued fields, but in the end of the day, modulo a diagonal action of the Lie group on itself here by right multiplication. That will be very important and very useful a little later. But for the moment, you may just note, okay, you write down an action with these two Lie group valued fields. What you can quite easily see is that if you reduce to the gauge invariant quantities by taking this combination of the fields G1 and G2, then the theory here, just on the classical level, reduces to the action or the theory that we have defined down here. And this is what is known as the Klimchik model. Klimchik has introduced this in this formalism, in this form, a good while ago, and has proven its integrability. Integrability is where? Well, we can either here, starting in the ungauged formulation, where we just have physical degrees of freedom, we can form some Lex pair. Well, actually, here it's more explicitly written in the gauge formulation. We can form some Lex pair, which has a complicated expression, but again, it satisfies the zero curvature condition.
What is the meaning of the angular bracket?
The angular bracket is just the invariant scalar product on the Lie algebra. You see here, everything is Lie algebra valued, and we're taking here Lie algebra element and scalar product with Lie algebra element.
Excuse me, can you repeat this? On the first line, R sub G1 and R sub G2, just any arbitrary matrices from the Lie group, right? On the first line.
You are
G1, G2.
Yes.
It's two arbitrary matrices, right?
Yeah, G1 and G2 are two arbitrary matrices which represent the degrees of freedom.
Like on the lowest line, one R lost subscript. What is this? I just missed. You explain that.
No, I mean, this was the part I didn't want to explain in detail because I don't have the time to really walk through the details of this definition here. The point is just, okay, there's an action and there's an action which has G gauge symmetry, and that will be a useful formulation. So that is maybe what we will really need for the rest. Okay, I mean, I would rather suggest maybe to discuss details about the definition later because it would be going in an orthogonal direction than I want to go.
Yeah, but what's the meaning of this subindex of R?
The meaning of the subindex of R is that this is this element twisted by the Lie algebra, the Lie group element. I mean, it is twisted by this Lie group element G2. Good. This is what will be important. There is, I mean, okay, it is known basically, and this goes back, well, I mean, it can be related on the level of just the action to a model that has previously studied by Fateev, who did not use a Lie algebraic formulation to write it down, but it is equivalent on the classical level to the model Fateev had introduced as the dual to a model that often is carrying his name, namely a model of three scalar fields with exponential interactions. So he had proposed a duality relation of the Fateev model, the one with the three exponential fields, to a sigma model, and it turns out to be the same as the one we're talking about here. There's an RG flow of the sigma model. And good, it is an RG flow, of course, that is represented in terms of the parameters.
If you may comment, because otherwise I will be personally lost. The model, original model you will consider, is this, it belongs to the principal manifold, G cross times G?
No, I mean, the degrees of freedom are G. There's a gauged formulation. There's a gauged formulation where you take G cross G modulo G gauge symmetry in order to represent the same model as something with twice as many degrees of freedom by the gauge symmetry.
And it's the left and right invariant.
I mean, the type of action was specified here. That is the gauge symmetry. So this is the gauge symmetry by which you divide.
On the right.
It's the right action.
Not the left.
Right. It's on the right.
But it's not a coset, right? So
No, it's
it's a coset.
that's what it is. Or you could call it a coset, yes.
But the action is more complicated. It
Is it
includes parameters.
non-linear sigma model, usually fixed by manifold.
Yeah, the manifold is
It's a
the
manifold.
manifold.
Group manifold.
Yes.
Or a coset.
I mean, it's not a standard coset. The degrees of freedom are group elements of SU2 D group. And here we're, as a second equivalent formulation, introducing a formulation where we take two Lie group valued fields modulo this particular action on the right.
A coset.
Yes.
The group manifold can be represented as a coset. Group manifold G is the same as G cross G slash G.
Cross G, right diagonal coset. That's what you would often call. Okay. Good. So this is how it looks in the UV, and in order to go into the UV, we have to figure out what is the renormalization group. I told you the two parameters are epsilon1 and epsilon2. They would be running under the renormalization group, and this has been figured out by Fateev, and the resulting formulae are like this, where we have here a parameter nu, which is constant with respect to the renormalization group, and you can take here as renormalization group parameter the kappa. Okay. The conformal limit, the UV limit, would correspond in this way of parametrizing the flow as the limit from above, no, from below where kappa approaches 1. And to have a picture how the target looks in this limit, I mean, it's a deformed, I mean, we have produced a deformation of the group manifold of SU2. Yeah, maybe this picture can serve. So we can parameterize it in terms of 3 coordinates called here phi, chi tilde, and alpha tilde, or here phi, chi, and alpha. And if we would fix, for example, one of the variables, a chi tilde, which is an angular variable, then it would look like a cigar. If we fix phi, which is like a Liouville direction for some, then we have basically a cylinder with these identifications here with respect to alpha tilde and chi tilde. So, I mean, in some sense, the intuition that it is somewhat similar to the cigar, but a 3-dimensional target space that may be helpful. The details, again, won't matter for the rest. Okay, so now we change gears and introduce a larger class of sigma models a priori, which are called affine Gaudin models, and they have a long and nice history. So it was the story was started by Fagin and Frenkel, Vicedo, Del Duc, Lacroix, Margot, Vicedo, Sylvain Lacroix, who is here, and so on, have developed this much further. And yeah, it uses this Lie algebraic background in order to construct and parameterize in a beautiful way quite large family of models. And we will find the model of interest here as a particular case thereof. So it will be, so here we're generalizing much further, but it will be useful, well, as an indication towards generalizations and as a framework then for studying the models of this class. And I want to explain why. But okay, for the moment there are a few a bit maybe abstract looking things. The point is, well, the Lex connection typically as an important parameter, the spectral parameter. The generalization concerns the analytic properties of Lex connections with respect to the spectral parameter. And the basic function encoding in a nice way all the parameters of the model, that is here this function phi, and it is parameterized in a way where you see the k, which corresponds to h bar, is in front. And then basically, well, we can take as the parameters, well, either the zeros or the position of poles of this function. And in the end of the day, for example, our epsilon parameters will be functions of the parameters in here. Right? So the physical parameters are all here in this formula.
Is this what they call the twist function in
This
the
is what is
literature?
called the twist function. Thanks. Yes, I wanted to. That's the terminology. Good. Then in order to introduce the kinematics, we have to introduce something representing the degrees of freedom. This will be a collection of Kac-Moody currents. We will have m+1 of them, and well, they come in pairs with a plus minus, which will have some correspondence to the chiralities in the conformal limit. There are some parameters which will be RG invariants, which are the levels and which can be defined as the residues of this shift function. So again, the spirit is everything is contained, I mean, all the parameters that are interesting are in the shift function. And in order to introduce the Poisson structure, we write down just the Poisson-Kac-Moody algebra. So thereby we have defined a Poisson manifold, a Poisson space, as the basis for all definitions. There's then a gauge symmetry which is generated, so it is again a gauge formulation as before, but now in the Hamiltonian framework. And we write down the Hamiltonian generator of the gauge symmetry, which is basically the most natural one, the diagonal combination of the currents. Okay, in order to define dynamics, we are to define Hamiltonians. And again, I mean, maybe details will be hard to digest in finite time, but the point is, again, we're taking here a combination which basically is just a very natural combination based on the geometry here of this Riemann surface C0 2m plus 2, which is just where the shift function is holomorphic on. And good, here you see the currents. We form a linear combination of the currents. We form something quadratic out of the currents. And we're integrating over space. And that is giving us a generating function, well, ultimately for conserved quantities. But if we then extract residues, it will give light cone Hamiltonians in the two chiral directions. So that's the scheme of things, that's how it works. But yeah, again, the basis is all nicely Lie algebraic. And integrability generalizes to this setup. Again, the formalism that was developed by all these people I've mentioned here would then allow us to write down the Lex pair very easily. It takes here this nice form where again you basically see, yeah, I mean you see that, well, we have, in this case, we have then the poles of the Lex connection at the position which were the zeros of these guys.
So just to be sure, what is meant by Gaudin model here is not the spin chain like Gaudin model, it's a field theory.
That's right. So it is a field theory, and this is why it's called affine Gaudin models. So this was the original philosophy of Fagin and Frenkel. They were basically very much inspired by, okay, having studied long enough, the ordinary Gaudin models and their Lie algebraic generalizations, and then they basically asked themselves, okay, what if we replace the finite dimensional Lie algebra, which defines the spin chain, by an affine Lie algebra, and that's the result, ultimately, after further developments. Okay, so there's a Lex matrix, and again, basically, it's just built out of the ingredients that we have seen, and it very much sort of inherits the analytic structure of this shift function. Good. Now just here, basically in a few lines, the statement about how to recover the Klimchik model, which is the model we started from. Namely, all we need to do is basically to identify these parameters z1 and z2. Well, we choose here the parameter m, which was basically giving the number of poles or the number of zeros. We choose it in one of the most simplest ways, and then the positions of poles that we have are parameterized in terms of epsilon 1 and epsilon 2, and the claim is, which of course requires work to be proven, that then this affine Gaudin model would recover the Klimchik model, the gauge formulation of the Klimchik model, to be precise. Okay, so this formalism is also useful and in order to describe some of the quantum aspects, it turns out, but non-trivially so. And here we're again relying on beautiful work of several people, but this result is due to Del Duc, Lacroix, Svetsos, and Siampos. So there is a formula, so phi, recall the shift function, contains all the parameters, and we can elegantly write the one-loop RG equation as an evolution equation for the function phi. And it looks like this. There's a new function f appearing here, which, okay, by a recipe that I don't give here on this slide, is built out of the original function phi. So that's not a new object. There's a formula basically expressing f in terms of phi, but it's a little more complicated. So RG equation is an equation for phi. And in this context, it turns out, I mean, this is something that you basically, for the Klimchik model, can just check by using this change of variables and using the formulae for the RG flow of epsilon 1 and epsilon 2 that we have seen before. And in general, it is at the moment, I mean, so one can correct me if maybe the progress has happened, is in general a conjecture, but which had been checked in some simple cases by numerical computations. So the point is that in this parameterization, the our G fixed point has a very simple description. It corresponds to Zi plus going to 0 and Zi minus going to infinity. So it's kind of beautiful. So plus and minus infinity of this spectral parameter Riemann surface is related to the chiralities of the model. Good. And then you can see what happens to the lag structure, to the integrability in this parameterization, namely by rescaling in a very simple way the spectral parameters, you get lax matrices that stay non-trivial in this UV limit. But the interesting thing that happens is, well, you can only keep one of a non-trivial form, whereas the other one is gauge equivalent to 0. So this, okay, if then, say, with this being said, you look at the zero curvature condition, you will find that this implies the chirality, say, of L plus. But I think it's very obvious. And you can do a second similar limit for the other chirality. So in this way, you see in this formalism Y in the UV, the two chiralities decouple from each other, which is of course not at all surprising, but it is kind of nice to see how this formalism exhibits this. Okay, so in the following, what we will do is to focus just on this chiral theory, and the goal will be to quantize it. Okay, so that's sort of a philosophical slide about sort of the type of approach that we want to propose, that we have proposed. So, I mean, typically, of course, traditionally, you start from the classical limit and try to deform away from it. And, well, this is what we call quantization, but this is also what, where then this non-ultra locality problem stated at the beginning hits us very badly. We could alternatively have the idea to start from the conformal limits. This is, of course, not at all a new idea. This is the whole philosophy of, for example, the approach of Baranov, Lukyanov, and Lochikov, who, motivated by such kind of ideas, started to study the integrable structure of conformal field theory. And my understanding is their hope was that this can be a useful starting point also for massive integrable field theories. By basically, yeah, once you have understood the conformal limit, you can hope that integrable structure deforms nicely in the massive direction. I don't want to deny that this philosophy also has severe difficulties, but nevertheless, I would say it still has yeah, it has some appeal, and I think, well, I think it is worth trying, in particular, what it can do for us in the case of sigma models. That's the idea. Well, the key point, a bit more technically, is that if we have these chiral structures, so left and right moving degrees of freedom, nicely decoupled, current algebra structures, and so on in place, that can facilitate the quantization, of course, enormously, because we know how to quantize Poisson affine algebras, and then we can try sort of to build everything on that. So that's the philosophy, that's the approach, the strategy that we want to apply. We want to first understand the integrable structure at the conformal limit, and the hope, but that is not, say, part of our work as yet, is that it can be useful starting point for the deformation away from this conformal limits. All right, so now let's go, unless there are questions about this, go into the technicalities of that a little bit. So, as I said, we don't have any difficulties to quantize Poisson affine algebras. These give the standard affine algebras, and I think everybody will know how they look like, so they're written here. That's the result. This is for now the quantization of each of the currents, which after all appeared as basically the residues of poles of the Lax matrix. Okay, it's also not so hard. I mean, there was a constraint representing the gauge symmetry. This was just generated by the diagonal combination of the currents. Good, we can form the same after quantization, and what this then gives is I mean, if I require on the quantum level the invariance with respect to the diagonal combination of the currents, the resulting VOA would naturally be defined as a coset VOA of this form. We're taking the direct sum of all the affine Lie algebras and divide by the diagonal action. Here is how the corresponding parameters k that we call level look in terms of the classical parameters. There is some h bar correction, but okay, let me not go into this so much. What is beautiful, and that of course now is one of the first sort of important steps towards really understanding the integrable structure, is that there is a very nice proposal for how to construct local conserved charges, exploiting this framework of the affine Gaudin models, and thereby sort of taking advantage of the Lie algebraic structures which underlie it. So here's basically the formula. I mean, it's a bit complicated, and maybe I don't want sort of, again, to walk you through all the details, but maybe to give you the flavor or give you the idea of how it works is the key ingredient here is, well, a family of currents labeled by the spectral parameter Z, which one has to find a solution to a certain set of constraints that Lacroix, Vicedou, Young have written down, and which takes the form that we're taking here some normal ordered product of, say, the basic currents, so some expression which is linear in the currents, so it is this generating function gamma that we've seen before, from which, for example, we could construct the Hamiltonian. There is some function p here, which in a sense is just a primitive of the shift function, so it contains not more than the information that is in the shift function, namely, well, the position, the ZRs were the poles of the shift functions, the Ks are the level parameters, and so on. So it is this information that was in this shift function. And then, yeah, we have basically to take a double integral. So here we're first integrating over space to get something only dependent on the spectral parameter. And then here the integration is basically in the spectral parameter plane along a Pochhammer contour. And the non-trivial, I mean, there's something quite non-trivial here about it, namely which is to formulate the conditions under which linear combinations of this form, right? We have here some finite set of parameters entering, and there are some dots here which give terms of lower number of the gammas and maybe a higher number of derivatives. So these coefficients have to be fixed as solution of a set of conditions which then these people here have shown to ensure gauge invariance on the one hand and mutual commutativity on the other hand. The conjectural aspect of this is whether or not this generates infinite, I mean, whether this set of conditions, which is very well formulated, has an infinite set of solutions, and therefore it would generate all of the conserved quantities, whether all can be written in this form, right? All right, so that is a...
Sorry, I missed that. Well, the tau is not just an invariant element of the Lie algebra, it's some coefficient that are...
Well, of course, there's an invariance condition with respect to the Lie algebra that will follow, that will be necessary for gauge invariance in particular, but for the moment it's just a coefficient. Right? So now, okay, just important to keep in mind, we have these two formulations of the Klimchik model, one just using physical degrees of freedom, which is the G SU2 group element, the other is gauged, so we have twice as many degrees of freedom, Lie algebra action and so on, and we're in the Carroll limit. So technically, and I really don't have the time to go much into technicalities of our work, the key point was simply to do a comparison of these two formalisms, which was important because, in fact, just in the purely ungauged formulation, the original Klimchik model, there is a lot of really nice and substantial and impressive work on the Klimchik model by Bazhanov-Lukyanov and Bazhanov-Gleb and Lukyanov, On the other hand, sort of now our starting point is this gauge formulation where we have affine Lie algebra and so on as the basis for the formulation. So the technical results, or two of the technical results that are important for us, is on the one hand to show that when we do the gauge fixing of the AGM Lex matrix, then we find the chiral limit of the Klimchik Lex matrix that, for example, Bajanov, Kutuzov, and Lukyanov had been studying in the ungauged formulation. And as you can imagine, the problem is a problem of computation of Dirac brackets, because we have to compute what the Poisson brackets of Lex matrix elements become when imposing the gauge invariance condition, and that was non-trivial. And the other is, we have two ways. I mean, in the work of Bajanov-Lukyanov, there has been a computation of the quartic charge, and this we compare to basically what comes from this formula. And it works, and that is, if you look at the expressions, I think one can consider it as a quite non-trivial check that these two approaches or these two formulations are in fact quantum equivalent. Okay, so this is the technical, this is sort of the brief statement of sort of the main technical things that, or some of the main technical things that we were dealing with. It's not, there was some more. But but now I want to sort of speak about the applications, the spirit being that knowing that we now have sort of two formulations that are equivalent on the quantum level, we can go back and forth and we can exhibit aspects of the integrable structure in the formulation that is most convenient for us and carry it over, say, to the other side by the equivalence. So what is nice about this formulation as affine Gaudin models is in particular that there is a quite far-reaching conjecture about how to represent the spectrum of local conserved quantities in the chiral limits, which goes back to Fagin and Frenkel and then was generalized by many other people. Of relevance for us are in particular works of Bajanov-Lukyanov and Lacroix, Vicedo, and Yang. So let me state the conjecture in a very brief way, but again here I'm touching on a huge and nice story in its own right. So the statement is, well, we're talking about the integrals of motion of the local IM that were previously defined with a formula like here, so maybe this structure is worth keeping in mind a little bit. The ODE IQ of T correspondence relates it to a problem in complex analysis or in the theory of holomorphic differential equations. And it says that there's a one-to-one correspondence between the eigenstates of the quantum affine Gaudin model and differential operators of this peculiar form, where this function p is again entering, the function p, which has appeared already several times, which basically is constructed from the shift function. And then there's a function which is, so this is fixed by the model. And then there's a function which has to be found, which encodes the information about particular eigenstates of the model. And we're stating here a problem to find such functions which have specific analytic properties. Well, it is allowed to have second-order poles at ZR with fixed residues. This describes, say, the modules in which we are finding eigenstates. And further, we allow singularities, additional singularities, around which the monodromy of this differential equation should be trivial. So these are so-called apparent singularities. And it can be shown that this triviality condition of monodromy implies algebraic conditions for these numbers, which are sort of our undetermined data. And this is a bit like equations of beta ansatz type. And it is conjectured, in some cases proven, that they have a discrete set of solutions in one-to-one correspondence with eigenstates of quantum integral models. So
So what are the numbers here? N, is n becoming large, or is it just
The
n
numbers
number?
here. So
The degree of
okay, yeah, good. This here is a bit more general. So n in our case will be 2. Because this is the number of poles for Klimchik model. This is a bit more general statement where we have n such poles.
Okay.
It's arbitrary. So this will be related sort of to the level in the model in which you are.
And that might be large, or
It can be large, can be as large as you want. So this is one of the, say, discrete data labeling the eigenstates is basically related to the K. Okay, so this is a problem which ultimately determines a discrete set of solutions for this potential V. You take it, you form out of it a certain differential polynomial, which I was not able to write down here, or, well, there's a whole collection of those which you can form. So there's a recipe to construct them in such a way that they do the job. And then you plug it into this expression, and out comes, that's the conjecture, the corresponding eigenvalue. Right, so the discrete set of solutions for these potentials V gives a labeling of the eigenstates, and if you want to have the eigenvalues, you just plug them into this formula, and this formula, of course, has not accidentally a clear, oops, no, this was it, similarity to this, right? We roughly replace this here by this differential polynomial Vp. And this is one of the sort of very beautiful aspects of this AGM framework. That is okay, so this is one application. It basically says, good, using this framework in the Carl limit, there is a very powerful, although to some extent still conjectural way to characterize the spectrum. This concerns local, I mean, so far what was said concerned local integrals of motion, but we learned from Bazhanov, Lukyanov, Samlochikov that non-local integrals of motion can be very important for exhibiting and the integral structure. There is, I mean, in the original work of Fagin and Frenkel, there were some recipes for how to construct non-local integrals of motion. But I think this was, this wasn't quite very complete in the sense that they didn't have at the time, to the best of my knowledge, a proof of the commutativity of the non-local IMs that in the AGM framework can be constructed. There's a very nice and for me really striking conjecture of Bazhanov, Kutuzov, and Lukyanov from 2018, which suggests a solution and which now, sort of in our philosophy, I want to discuss here. This is, of course, not our contribution, but in the framework we're working, basically these results, thanks to the correspondence or equivalence between gauged and ungauged formulation, it can be carried over to the AGM framework, the affine framework. So, what's the statement? We can basically, out of the fields of the sigma model in some convenient coordinates, and there's some details here which we don't have the time to discuss, we can form screening charges like this. So you see the characteristic form, there's some derivatives of the fields here, and then some exponential, normal ordered exponential here. And you see the parameters K1, K2, K3, these were the levels of the currents. You see them built into this expression. And then you're integrating just over space. This is what is called screening charges. It's a fact that polynomials formed out of these screening charges can be renormalized such that the path-ordered exponentials, which are a priori, of course, just very formal expressions, make sense as a formal power series in these screening charges, and in the sense of formal power series satisfy Young-Baxter equation. Like here, okay, you will know. The point is, I mean, what is behind, I mean, all you basically need to convince yourself of is that you can renormalize, and this is here a bit more tricky as compared to the original case of Bazhanov, Lukyanov, Samlochikov, because these fields here, these currents have more severe short distance singularities. but there's an argument in our paper indicating that there exists a renormalization such that these guys satisfy the Serre relations of the quantum affine algebra UQSL2 hat. And then one can appeal to a beautiful argument that goes back to Bajanov-Novikov, but really sort of maybe the nicest version is in a paper of Bajanov, Koroshkin, Hibbert, which just based on the fact that these guys satisfy Serre relations, you can conclude that as a formal series, this quantum monodromy matrix satisfies the Young-Baxter equations. Right, so that is nice, but there's more in what is conjectured of Bajanov, Kutuzov, Lukyanov, and sort of it is now that is becoming really striking. A conjecture that the such defined matrix admits a classical limit in which the classical monodromy matrix that we had formed before, that we had seen before, reappears. However, with some twists. Note, we have here simply introduced in a kind of standard fashion a spectral parameter lambda. So far, we've always called our spectral parameters Z of lambda, and part of the conjecture of Bajanov, Kutuzov, Lukyanov is that the renormalization effects that occur, that are relevant for taking the classical limit, produce here a non-trivial function Z of the spectral parameter lambda. There's an explicit formula that these authors propose for the function Z of lambda. I mean, yeah, it is clear that this limit is very subtle, and well, we hope maybe in future work to be able to study it more and to actually perhaps prove it someday. Because it seems, yeah, these renormalization effects are not completely outrageous and uncontrollable. But yeah, for the moment, this is a conjecture. If, however, you accept that this is true, this conjecture, then it would establish that there is a very intricate way around the non-ultra locality problem. Namely, despite the fact that the non-ultra locality creates a serious problem for even defining the Poisson structure of the classical monodromy matrix, its quantization can have simple commutation relations of the Young-Baxter equation type.
Is it possible to somehow take back the classical limit now from this good quantum monodromy matrix?
Yeah, this is. I mean, this is what the statement of the conjecture is about, right? So,
I mean,
you're going only from quantum to classical. You happen to have found something that is well defined and meaningful in the quantum theory, and it produces the right thing in the classical limit. But what happens exactly to the Poisson structure is difficult to say because, because of all these renormalization issues, it is not even easy to say whether in the classical limit the quantum computational relations do apply a Poisson structure, at least a Poisson structure of any standard type. So it means that somehow the quantum theory is nicer than classical theory would allow us to expect. Okay, so I think this is, I want to state it here basically as an application of these equivalence between gauged and ungaged formulation, that these kind of things carry over to the context of the affine Gaudin models. And furthermore, as a, important direction for future research to understand what's going on and what we can do with it in the future. Okay, well, maybe how I'm doing with time, I may be faster than I thought. So that's the summary slide. So let us just compare sort of the virtues and perhaps drawbacks of the two formulations. So the affine Gaudin model formulation, which basically can be seen as a formulation as a spin chain with affine Lie algebra symmetry, that is good for describing the quantization of the algebra of local observables. So for as carriers of the degrees of freedom, we have a W algebra or some vertex operator algebra. And then there is a recipe for the construction of local conserved quantities, which is heavily based on this Lie algebraic structure underlying the affine model formulation. And furthermore, the other key ingredient there is that we have somehow the nice complex geometry of the spectral parameter Riemann surface being built in a nice way. So that was all included in the shift function. And what this helps understanding is the RG flows along with the construction of local integrals of motion. And in the end of the day, thanks to ODE IQFT correspondence, it helped understanding the spectra. On the other hand, so this is sort of the local story, and AGM formulation is good for the local story. It appears that the ungauged formulation is good for understanding the non-local conserved quantities, because there is the conjecture of Bajanov, Kutuzov, Lukyanov, in what is, and all the hopes that this raises, which indicate that there we can take advantage of the relations to quantum affine algebras that are familiar from integrable models that are not of the sigma model type. And yeah, ultimately, one can hope, but maybe you may want to rather call it a dream, that these structures do admit deformations away from the conformal limits. I mean, I would say at least in non-sigma models, there are some supporting evidences that this is not outrageous once you have Young-Baxter algebra structure in place. That's another big step to be taken, of course. Good, thanks.
Any questions?
In the classical case, usually all this integral model has alternative formulations through Baker-Heiser wave function and position of its singularities, or through the Riemann surface associated. Does this problem have it? Does this model have it?
Well, I think I understand what you have in mind. This, to the best of my knowledge, has not yet been developed in any detail for this class of models. So, these finite zone integration and so on, right? It might be interesting to see if, for example, there's a nice interplay with this affine Gaudin model formulation. So I think on first sight, it sounds like an interesting suggestion, yeah.
And one more, on the same level of educational question, is there any beta ansatz, sort of, or
Beta ansatz, yeah, not yet. There was a beta ansatz of a sort through the ODE IQFT correspondence. The traditional beta ansatz would, of course, be different. Would need to, for example, discretize, but personally, I would think the discretization should rather maybe use then some non-compact lattice degrees of freedom, so you would rather expect something like separation of variables to be relevant than beta ansatz.
If I may comment just on that, there is actually algebraic beta ansatz in the case where the Hilbert space is built as highest weight representation of the affine Lie algebra.
Well, yeah, okay.
And then there's a reference state, and then there's really an algebraic beta ansatz which is known and which is exact. I mean, which at least, for instance, the quadratic Hamiltonian.
Yeah, these are these sort of bit more fancy beta ansatz where sort of you replace what used to be the Lie algebra by the affine algebra.
Sure. Yeah.
So
for instance, you need to lower also along the affine direction.
yeah.
Then there are some exact
related to stuff that Jimbo and company are doing. Right?
Could one approach the quantization of this model from this less rigorous but well-established approach of Paul and Polyakov to transform it first to Turing model by this transformation, etc., and then to try to solve it by beta ansatz or nobody tried? In
Uh,
principle, it's a sigma model. You could.
yeah, no, I think I know what you mean, but I don't think this has been tried yet, as far as I know.
Also, okay. The second question: are these models similar to what was considered, what were considered by Zeitlin, Nat Levin, the coupled?
Yeah, there is a. Right. There is a. I mean, it is related to. There's a whole zoo of connections to other types of sigma models. I don't know, Sylvain, you have a quick way of sort of summarizing the state of the art.
So I think if you mentioned the paper where they have this renormalization of
Yes,
G cross G model, yeah, then it's among the family of affine Gaudin models.
I see.
It's not exactly the same type of one. You realize the Kexman occurrence in a different way,
Mhm.
but it's also in the same family, and similar things should apply.
Okay, next. Yeah.
Sorry. Coming back to the previous discussion about beta sets. So you presented this ODE solution. No, I thought that the ODE solution is solution to some Baxter equation. No?
The ODE solution is not.
Originally,
Does not use the Baxter equation. Oh, okay. Well, good.
so if there is Baxter equation, there is beta ansatz. My question is beta ansatz the one which Paul was asking you about?
So far for this model, there is a first principle construction of the monodromy matrix, which I discussed, but I think this is as far as it was pushed. There is no Baxter operator constructed, and there's no lattice. This is not what you mean. And then the
No. Originally in this Bajana Malochkov
yes.
computation of the paper. So they wrote up in their paper Baxter equation, and then people figure out the solution to those Baxter equations could be parameterized by those of D.
Yeah, but this was what I just meant. This doesn't exist yet here. It hasn't been done yet for this model. So yes, would be very nice. And ultimately, of course, the dream is that you sort of, as for example, for sine or sinh Gordon, you have a Baxter equation. The Baxter equation you can translate into some nonlinear integral equation, and then you can show that what this does is equivalent to what the ODE does. In the simplest cases, we know sort of how to close this triangle. In this case, that's for the future.
So, because Paul asked questions, so it was reminiscent of something. And so there was a long ago, there was a paper by Fadeev and Reshetykhin, right? Where they quantized the principal chiral model using completely wrong Poisson brackets, but getting the correct result. Yes, so similar to that. So what happens here or not?
Again, I would love to know the answer. Sort of my gut's feeling is that, say, if we understand precisely sort of why this Bajanov-Kutuzov-Lukyanov conjecture is true, I think it should basically explain why this ansatz of Fadeev-Reshetykhin did work magically. That would be my hope.
So could this approach describe the usual principal chiral field or ON sigma models?
Well, it is part of the family of the parameters in this sense, yes.
So can you tell what is the UV limit, the conformal field theory of the principal chiral model?
Yes, but it is say something that we didn't, to be honest, look at very explicitly. Sort of our limit was making okay. If you take maybe the O3, so the two-dimensional case as a example, right? You have in mind the round sphere. What we understand quite well is where the sphere is deformed to the sausage, and the sausage gets hot and thereby very long. In the extent to which this can be used to understand this, which is a particular limit in the parameter space, one should maybe study carefully to be on the safe side. I mean, I wouldn't want to make big statements without studying it.
Okay. Good. Coffee break for a question? Well, one last question then.
So I have a simple question. Much simpler. So you start with Lie groups and then you pass through Lie algebras. But so what is like if you are considering like the model with the simply connected Lie group, the joint Lie group, or so what is like
I understand your question. It's an excellent one. Let me rephrase it in my own words. In most of this AGM formalism, one was only seeing the Lie algebra. At the end of the day, you want to use all this to build a model which is based on the choice of a Lie group. I haven't thought carefully about this. I would expect it is basically then hidden in some conditions on the spectrum of representations that one considers on the level of the Lie algebra. So whether the affine Lie algebra representations that appear here, admit an exponentiation to this or that form. Right.
Okay, good. So let's thank Jörg again.